I'll be now taking up on is looking into CAN security. So what specifically can we do on the CAN level? But I'll also try to pull together some of the strings and threads that you, Manuel, and Axel have thrown out as us, and review and see how they fit together here when we look at CAN. Now, for those of you who don't know me, my name is Olaf Pfeiffer from the Embedded Systems Academy. And together with my partner, Chris, we've been quite busy publishing several articles, books, and more. So here's just an overview of some of the related publications. And specifically in the CAN newsletter, Chris and I had several articles giving you updates on CAN security and CAN security aspects. So yeah, quite busy in that scenario. For this presentation, I'll primarily look into the specifics of CAN. So we'll simply pick a typical CAN bus example and show the potential attack vectors, and then summarize the CAN-FD security solutions that are already available today and do a comparison of them to see, one, do we apply which of them, and give you some recommendations on how to best combine them. This presentation is based on a paper that together with Andreas and Axel, we presented at the last International CAN conference, and it's just updated with a few slides to show you the latest points and developments. If we took a look at a typical CAN system, let's just pick any fictitious electric mobility device, maybe a wheelchair or something like that. Then what are the components in there? We'll definitely have a lot of CAN connected controllers. There'll be things like a joystick, a drive somewhere, maybe a battery system. And specifically from what we've seen now in the last presentations for hackers of interest, of course, is any connection going out of the system. So is there anything that is connecting us to the outside world or to even to the internet? And so for anyone who wants to attack such a system, there are really tons of attack vectors available. And if you ask me why haven't we seen much more greater and publicized attacks like some of them like Manuel has presented earlier, well, I would say we were just lucky, because in CAN we are really in the current situation that quite a lot of systems simply do not have these sort of interfaces. And of course, for any hack to really hit numbers or press or media, it would need to be applied to lots and lots of systems in parallel. And this could only happen if maybe there's out there a popular gateway that is then hacked, and so suddenly we get access to millions of installations of CAN systems. So literally I'm checking once in a while. My partner Chris has to do quite a bit of shopping also on Alibaba, and I once in a while look there if there's yet another simple, easy to use CAN wireless interface, and you'll sometimes see dongles that you can use for your OBD onboard diagnostic port in automotive applications. They start, I think they were already less than 10 euros, and provide a wireless interface into your OBD port of the automotive section. And hey, this comes from Alibaba, a no-name manufacturer. You have to install a no-name app on your phone. Just imagine somewhere in the industry, this would somebody use in a similar system to say, oh, it would be really convenient to get access to some of my data from anywhere with my phone. And suddenly we are opening a door where such a device, when popular and installed in many systems, would be a real threat, not only to a single system, but to really a lot of systems if applied and connected to a lot of systems. Now, the biggest threat for anything in CAN and attack is, of course, what we define as unlimited physical access. Because if you have physical access to the device, and literally unlimited, meaning that you'll be able to dissect the electronics, then it becomes very hard to go into protection there, simply because there are services out there, that if you search a little bit, you can send in your microcontroller that is completely locked and the code is not accessible, and maybe there's a key somewhere in there, and they will unlock it for you, send you the code, send you the keys, literally for an ARM, meaning, well, it doesn't cost you more than a few ARM processors. We had a customer who did this with an older microcontroller. They inherited code and the developer died. They really wanted to get access to the code. Well, they sent in the microcontroller to one of these cracking services, and literally they only paid $100 and got the entire code within a week. Now, of course, this was an older microcontroller. With the latest microcontrollers, and specifically those with specific security functions like the poof function that Axel mentioned, it will be much tougher. However, the point is that with unlimited access, an attacker has so many options also to go through side channel attacks, debug ports, other communication ports that a microcontroller might have, that once an attacker has this sort of access, I wouldn't really worry about the specifics on CAN anymore. So it's really about more protecting once somebody comes out from the outside, either with a sniffer, is able to read and write CAN messages from the outside. How can we protect our system here? And so there are quite a few technologies available that can be used on CAN already today, and those we'll have a look at. So for the overview of the solutions available today, we'll focus on a variation of 3 different solutions. And we'll here now have a brief overview and how they fit into the various layers. So this is not the traditional complete ISO layer model. I really have this more structured as we see it in typical CANs and programming layers that we'll find. So it's not really your traditional network layers all the way up here. However, if we look at it on the CAN level, then down here we have somewhere our physical and data link layer where all the CAN is implemented. And then somewhere in each embedded system dealing with CAN, there will be some sort of driver. And this layer will take single CAN frames from the data link layer and provide them to the upper software layers, potentially involving some more FIFOs, buffering, and so on. If we look further up, then if there's a protocol stack involved, J1939 can open or anything homebrew, then at this point there will be some layer where we look at single messages of this protocol message layer. And at a little bit higher layer, there will also be message sequences, so multiple of those. And somewhere on top, of course, we have an application layer. Now, looking at the different solutions available, then we have something called hardware ID guarding, and I will go into the more specifics on all of these solutions a little later here, but that hardware ID guarding sits really here directly on top of the data link layer. Then we have software ID guarding, which would be part of the driver layer, really doing the same thing more or less, but in software. Then we have the CAN crypto layer. So these are all solutions that add some cryptology methods to individual CAN frames. These also sit here in the driver layer. And then somewhere, as Axel brought up, the datagram transport layer security, this sits more here on the upper day because it involves definitely message sequences. So to get a single DTLS message communicated from one application to another, we definitely need to pass on several sequences. It will not fit into a single CAN message. So let's take a closer look at the different technologies. And let's start with the CAN ID guarding. Now, the idea behind CAN ID guarding, and I assume everyone here has enough basic knowledge on CAN, otherwise you wouldn't be joining this group anyway. But to really make sure that everyone here is on the same line, allow me to repeat that one of the essentials in any CAN communication system is that each and every CAN frame has somewhere a CAN message ID. And for our purpose now, let's assume the regular 11-bit CAN identifier. So you have 11-bit of CAN IDs, and these CAN IDs are assigned in your network uniquely, meaning the same CAN ID is typically, of course, there are always some exemption in some protocol somewhere, but in regular operation, you would expect that each individual CAN ID is only used by one specific device. For instance, if there's somewhere a CAN ID that holds my X, Y, and Z position of the joystick, then this CAN ID will be used over and over again and only by this joystick. Nobody else has the authority to transmit this data. So now the idea behind the CAN ID guarding is that in a CAN network on a system layer here, we will know all the CAN IDs used by these devices. And in almost all systems, again, there are a lot of exceptions here and there. These will be fixed. There are implementations where CAN IDs can be dynamic and change during runtime. But for now, let's assume they are all fixed because that's really a majority of the installations out there. So if we look at these sort of installations and we know that, for example, the joystick message is always CAN ID 123, then whenever this joystick or the process running here doing this ID guarding, if this sees CAN message 123 coming from the network side, then this task will know, gee, somebody else is trying to use the CAN ID that is reserved for me. So we have really a quite simple way of detecting that there are illegal message injections, spoofing, replays attacks, if everyone monitors their own CAN IDs. So if each of these devices monitor the network for CAN IDs that are supposed to be reserved for them, then of course, as soon as somebody injects a message here, somebody here will recognize it. Now, the big question and difference between hardware and software implementations is the what then? What then meaning we detected it, so now there is the message out there. How do we react to it? The nice thing is, if we are doing it in hardware, and NXP has a secure CAN transceiver that can do this, in hardware, they can react instantaneously and actively destroy the message or the frame while it's on the CAN system and convert it to an error frame. And so nobody else will actually see this CAN message anymore, this CAN frame, because it is actively destroyed by this transceiver. A software variation would not be able to do it. A software variation can only react after the breach detected. So the software variation would say, oh yeah, I see somebody used my CAN ID, but what do I do now? Do I send an alarm, an emergency, a status out there? Do I shut down? Do I inform someone? That would depend a little bit on the software side. So we can definitely do much more on the hardware side and directly reacting to it. And while they are on it, NXP implemented a few more other things like transmission rate limiting. So imagine this joystick is turned into the attacker because maybe the joystick is taken over by an attacker. Then the ID guarding in hardware also ensures that CAN messages going out can only come at a certain transmission rate. So you could not use this joystick for a denial of service attack where you flood the CAN network with back-to-back messages of high priority, because this ID guarding transceiver would not even let the messages go out of the device. So in summary, we now have a protected circle here of this network segment or the CAN network, where all the devices included use the ID guarding. And as I said, this can be done in hardware or software. The nice thing here is, in comparison to all other solutions, is that there's no cryptography involved. So there's really the processing time, no matter if this is done in software or hardware, is absolutely minimal, because we really look just only at the CAN ID and react directly to the CAN ID we see on the network. Of course, the challenge a little bit is when and how to initialize these. There is some point in the lifetime of the system where these filters in these ID guards need to be set. Typically, you would do this at the level where the system is fired up the first time and plugged together. Here, one of the possible solutions could be to simplify things. For instance, in a software solution, we offer a simple variation where literally this ID guarding task monitors the messages transmitted by this device and then automatically knows, oh, if this device now transmitted this ID, we know this is an ID we need to protect. And so this is kind of an automated setup. However, this is not as secure as if it would be pre-set up, because if the code here is compromised, then maybe it transmitted data that it shouldn't be transmitting in the first place. Let me just review the slide one more time. If I forgot anything, no, I think I got most of it covered. Let's look at the CAN cryptographic layer. Now, the CAN cryptographic layers that are currently already available either as part of our CAN crypt, or there's quite a few other solutions out there. Also, AUTOSAR uses some CAN cryptographic layers. Then these all use, so as far as I know, as of today, shared symmetric keys. So they have to have all the same symmetric key installed here in all of these devices. And typically there is somewhere a method defined to update this key. And while CAN crypt can do this dynamically while running, other systems might require a power cycle, a wake-up sleep cycle, or something else to refresh the key. The methods used here for for the security AES 128, if available and supported by all of the devices. However, we can also run with lightweight block ciphers like Xtea or some others. There are some 64-bit lightweight block ciphers that are less prone to a lot of computational power required. So this is really depends a little bit on how much performance is available in the different processes here. The downside, so to speak, for each of these cryptographic layers is that we need a security record, some data. We at least need a signature somewhere, and often we preferably also have some status information. So what we need is, we need to be able to put some extra data somewhere in the CAN frames transmitted to include the security data. Now, for the future CAN XL, some of you, I know from looking at the list here of participants, are well aware of CAN XL and the definitions there. I didn't specifically include it here because this is really, well, not yet commonly available. However, security there is really handled directly. There will be quite a big additional data block added also to XL for the security, allowing really full-sized hash signatures to be transmitted. However, for both classic CAN and CAN-FD, this is really not an option. It always needs to be a compromise somewhere of how much data can we sacrifice, so to speak, for the security information. And this can go down as low as I have seen custom implementations where a single data byte is used in a classical CAN message to have some signature data. And what we do in our latest discussions with the generic security layer that is currently under discussion at the CIA, and I will talk about much more details there tomorrow in our presentation, is that for the classical CAN, we can also put this into the ID area. Now, most of you will know that there are also the 29-bit identifiers CAN IDs. So instead of the 11-bit I mentioned earlier, the frames can have a 29-bit CAN ID. And if an existing system is purely based on 11-bit CAN ID, then by switching to 29-bit CAN ID, we suddenly have 18 bits to play with. And these 18 bits can then be used to contain part of the signature and extra data, uniqueness data, and so on required to do the communication security, to add some authentication information to the frames. If we look at the specifics of CAN crypt, once the devices here are grouped, there will be a secure heartbeat. And just by monitoring the secure heartbeat, all devices know that they are still grouped and they are still using the same key. So also here, one of the potential recognitions of errors is not necessarily that a device directly transmit an alarm or an error, because if an attacker is fast enough, then the attacker might take a device down before it's able to communicate anything else. So if an attacker is really good and fast, they will try to kill individual devices before they can set off a potential alarm. And so something like a secure heartbeat is very important, because then if you lose a device and suddenly a device is gone from producing the secure heartbeat, then that might be the only indication that you get that something is wrong and your system is potentially under attack. Let's now also look in summary at the end-to-end security. So as Axel already mentioned, it provides quite a higher layer of protectiveness than we have with the cryptographic layer, simply because there are true full-size hashes, no truncation, no compromises. But on the other side, it will never fit into a classical or even a single CAN FD frame. There will always be segmented data on there. So the best use case for the DTLS is really not as much the communication directly within a system. That would, of course, also be possible. However, we see the real advantage here for anything leaving the system. So whenever we have some communication that leaves the CAN system and want to reach the outside world, then DTLS is by far our best option to ensure that we have authentication and potentially also encryption and proper security handling going in and out the system. And so this communication could be as well as directly to one access point only. Maybe there is something like a gateway to the internet or to the outside world, and you use DTLS only to communicate directly with that device. Or it could also go all the way, be tunneled through the CAN network with segmented messages. That is, of course, much easier if there's already a higher protocol layer like CAN Open or ISOTP, something that handles segmentation, and you can transmit larger data blocks in multiple segments. So as I said, this is best for everything leaving the system. Now, really the most time we spent together originally when we wrote this paper together with NXP, with Andreas and Axel, was this table here. Because this table really brings you down the essence of what each individual method is capable of, but also their limitations. So this table is really the essence of the security options available with the three methods. And let's really just go through them one by one because they are quite important and show you the differences. So the protection divided on the ID guarding is that we have something we would call local CAN domain ID ownership, and with the hardware also the busload limits. So we know, as we said earlier, CAN IDs are owned by the producer, and this ownership is, so to say, protected by doing ID guarding. The CAN security layers, like CANcrypt, provide multi-domain, so they can typically go across bridges, allow pairing or grouping of multiple devices, and the DTLS is remote access, secure pairing. So from the relation, from the ID guarding, we have one-to-many, so we protect more or less the entire network or multiple nodes with it. Also with the CAN security layer, because here we have also multiple nodes that can participate in the same group, versus the DTLS, which is always a point-to-point. So if you would have a lot of secure communication within a single CAN system, then DTLS might be an impractical choice. Simply, you would need to communicate everything one-to-one and repeat it over and over with multiple frames, so that might not be feasible. So if you remember, one of the first slides I showed you was the layers which are protected by each individual method. So the ID guarding is more on the data link layer or the lowest driver layer, so to speak. Then the security layer sits within the driver or just above the driver. And the transport layer security is really all the way at the top near the application itself. When it comes to keys, then we already said ID guarding has none. CAN security layer has a symmetric key, and the remote DLTS has asymmetric keys, certificates, public cryptography systems. So all the bells and whistles of modern cryptology is in here, whereas the CAN security layer is somewhat limited in the way that these symmetric keys at some point need to be initially installed, right? So also here, the typical place where to do that is directly before the entire network is switched on for the first time. Because typically you can't do it on a manufacturer level, because if you try to combine devices from multiple manufacturers, then it wouldn't make sense to share the same symmetric key with multiple manufacturers. That would not really provide for good security. We'll have much more about keys and how they shared and certificates and key management in our presentation tomorrow. So the root of trust with ID guarding is not really applicable, is more on a system design. I always say, speaking to you programmers out there, it's roughly at the same point where you sometimes have your code development. So if you develop a system where all devices are under your control, then you would put the root of trust probably directly into the code and put the ID guarding as part of your code. Or if not in code, then somewhere within the configuration. So within the configuration of a device. The best place for the CAN security layer is the system integration level. So that person who plugs together the CAN components and switches on the entire system for the first time is typically a good point for doing it. And the DTLS certificates are typically installed already. The first one, we saw the different levels that Axel shown, but the first one would already get installed directly at device manufacturing, so that a device can be directly linked and hooked up and identified to belonging to a specific manufacturer. When it comes to leaving the CAN network, then only the DTLS messages can. All the others are, well, theoretically, you could put them now about with ID guarding, not with CAN security layer. Of course, they could be forwarded elsewhere, but typically it would not make sense. So I will keep it at a no. CAN cross CAN domains. CAN domains meaning if you have a multiple CAN system, so that you have dedicated systems with bridges in between. Can they go across bridges? ID guarding can't. The CAN security layer with some limitations can. The MCU processing power required. As I said earlier, the nice thing with ID guarding is none or close to none. Even if done in software, there's no complex cryptography here. It's just really a lookup of CAN IDs, if it's a match or not. For the CAN security layer, it all depends on the specific block cipher chosen. Is it full-blown AES 128, which can be a benefit if there are hardware accelerators for it. But if the microcontroller does not have a hardware accelerator, then we might need to reduce to some lightweight block cipher. And of course, DTLS requires the public key methods and block ciphers used in those. Very interesting, I think, is the overhead. So we already said that for adding security, we need to add some at least signature to the CAN frame or the messages. So what do we add and what is the additional background communication to initiate and open channels, close channels, and so on? So for ID guarding, of course, it's none. For the CAN security layer, I mentioned the secure heartbeat. So that's a few messages. If you do a heartbeat of every 500 milliseconds, well, then it's these messages per 500 milliseconds, plus the messages for dynamic key updates. However, these key updates, theoretically, they could happen often. However, even with lightweight block ciphers, I don't really see the need to do it more than maybe once per hour. Typically, once per day would be good enough. And for the DTLS, for the initialization exchange of certificates, the last time we looked and measured, we were somewhere around 700 bytes here. Now for the data exchange itself, at the ID guarding, we are at none. For the CAN security layer, well, a few bytes. I mentioned before the challenge here with classical CAN is where to put it, and potentially the 18 bits CAN ID could be used. If you use a 29-bit system and all CAN IDs are abused, then typically the only thing that helps is, well, using an extra message or an extra frame, so that suddenly you would need to have something like a preamble that you transmit a CAN frame first. And then in this preamble, you say, oh, the next frame coming with that CAN ID, here's the security information belonging to it. And of course, this really stresses your communication, because if you would apply this to all of your messages, hey, you would just double your throughput. Well, not completely, because that would need 8 bytes, the preamble, but yeah, it would add a lot of overhead. So this really needs to be carefully evaluated when using the CAN security layer. With CAN FD, where we have up to 64 bytes per single frame, we typically use already 8 fixed size, 8 bytes for the security overhead. And for the TLS communication, once the channel is open and the initial data has been exchanged, then we are talking about 128 bytes of data per exchange. So it's, well, for classical CAN, yep, quite a bit. For CAN FD, we are talking 2 to 3 frames, depending on specifics. So it's still quite a bit. So you, as I said, you wouldn't do it for each and every communication. And if we look for the best four, then I'll cut this short a little bit because we have one more slide at the end talking about our conclusions. So yeah, when do we use what? Well, I think before making this decision, it's one of these that is highly application specific. You first have to identify what your security needs are. So first of all, what is your current weakest spot? If you know of your weakest spot and that's there, it might not be worth your time spending too much energy on a completely different other area of your system when you have some loose ends. A good example for CAN here are bootloaders. I don't want to spend too much time drifting off here, but existing CAN and CAN open bootloaders, we know quite a few bootloaders in commercial products that are as simple as once they are activated, send them the hex file with the code, they'll program it and go with absolutely no security checks. Well, this is how systems were developed 20 years ago, and there are still, well, not even 20 years, even 10 years ago, this was still more or less a common approach. So it wouldn't really help if you add on a lot of CAN security communication, but keep that old bootloader in place. And once that is activated, it's just easy, send a hex file there and do a reprogram. So really, you have to look at all the holes and attack vectors that apply to your system, identify the weakest spot, and then go from there, see what can you do about those first before you spend too much efforts on other things. Now with bootloaders, just to really tell you how minimum of a security issue this was, there are some CAN open standards, and I now don't want to put out these specific numbers because I don't have them in head by heart anyway, but we have CAN open bootloaders defined in some CAN open specifications, and literally what I just said is almost there specified as even part of the standard, so that even the way how to activate the bootloader is standardized. And so just by looking in the standard, you could see how can I activate the bootloader, and once it's there, okay, I can send my file. I think what we never standardized is the file format. So this is still manufacturer specific, but as I said, we know quite a few manufacturers simply choose regular hex files. So the other thing that you need to ask yourself is, well, what do you really want to protect most? So I didn't go into these specifics from the crypto layer, from CAN crypto layer, but typically you can configure the CAN crypto layer to either do authentication only or also enable encryption. And I can tell you from most CAN companies I talk to, encryption is seldom an issue. It's more about the authentication. So encryption is typically only for those who really want to make rebuilding their intellectual property and use it also as a part of copy protection, that the data communicated is encrypted so that it becomes more difficult for attackers to figure out where which data byte is and so on. So yeah, if you do intellectual property and copy protection, then you might need to be using encryption also. However, often I see it's really just about authorization. Does a specific node have the authority to demand a specific protocol or command? So that can be done typically then without encryption. Sometimes you need to specifically protect user data, even if it's on CAN, maybe in medical machines where data is collected. And another point might be reusability after theft. So also here, this is kinds of intellectual property protection. So if your wheelchair that we talked about, gets stolen and somebody removes all the components, can they quickly reuse them? Or maybe if every CAN communication in there is locked and encrypted, it becomes useless to them. So review those carefully, and then you would need to make an independent decision in your system to how to prioritize and where to start with the various protection layers. Some overall recommendations. Number one, really, because it makes the life for any security measurement that we are taking so much more complicated, try to avoid the dynamic use of CAN IDs. I mentioned earlier that we all know in CAN systems that CAN IDs are assigned uniquely. However, there are some CAN open profiles and systems where those can change during runtime. And there's some authority out there that can say, oh, device number 5, for this and this purpose, you can now use CAN ID 234. And although these sort of systems, of course, have their right of existence, there was some reason to implement it that way, it really complicates the security aspect. So for any new decision if you design a new CAN system and you have to review the decision, do we want to use dynamic CAN ID usage, and you take the security aspect into consideration, then the outcome might be different than without taking the security aspect into consideration. So that's on dynamic CAN ID usage. On the ID guarding, the nice thing with the ID guarding is that it's really so simple that also on a software layer, that if you are not willing to go now for all your devices immediately for the secure CAN transceivers, well, at least consider doing it in softwares. It's really one of the first and easiest step. Literally, as I said, the very first easy implementation could be that whenever you transmit something, add this identifier to a list, say, oh, this is a CAN ID that I use for transmission. And when you ever see this CAN ID coming back from the network, trigger whatever your alarm event is saying, okay, something is wrong here. Somebody else is using my CAN ID. And this is really in software so simple that really everyone should do this as a first step. The nice thing about the CAN cryptographic layer is that not all of the nodes need to do it. It really is good enough if those that participate in the secure communication do it. So you can really choose the specific frames, messages that you want to protect, and only protect those. And as we said earlier, whenever you have communication that leaves the CAN network altogether and goes somewhere to the outside world, then this should use DTLS. This is the overall recommendation. As Manuel said, there is no silver bullet that fixes everything. You always need to review your own use case. But if we look back here at this wheelchair or electric mobility device, so what does this really mean? What can we do? Well, number one, I don't think I'd mentioned this before, but try to avoid easy direct access to any of your internal CAN networks. I mean, physical access. Because if you, for instance, say you have a charger or a diagnostic device or whatever that you allow to plug in to your internal network, then this is a sort of dynamic that also in security we have to prepare for again, because this means that the CAN ID potentially used by this device and that are allowed directly on this CAN network are not always present. We suddenly need to add a state where we say, well, in this state it's allowed, in another state it's not. So therefore, the recommendation is that you always use a gateway for everything external. And just if you compare this to automotive, this is why they came up years ago with the onboard OBD device port, and the OBD port was originally also designed to be a single point-to-point communication, because it was always also designed to be a firewall into the vehicle, and it was to protect the internal networks from direct access. So of course some manufacturers might have ways around it and specific operating modes where more data gets through, but in general the idea is, so whatever you connect to the CAN networks, try to avoid direct connection, put something in between, a gateway, a bridge, whatever. Then, as we said, ID guarding is so easy and simple. Try to do this as much as you can to protect your individual domains or parts of the system. So those can go here. When it comes to the cryptology or the CAN security layer or cryptology layer, then these can be in selected nodes. So here in this example, I chose a joystick, so direct drive commands and status coming back from the drive, as well as the gateway obviously would have to have secure communication. LEDs I added maybe for the display of an alarm LED or so on. It's just an example to give you an idea. And then, of course, as we said earlier, whenever communication leaves the entire system, so in this case, if we have a wheelchair, everything leaving the wheelchair should have DTLS involved, so that you do not directly communicate any CAN frames on this layer. So I think I'm coming also to the end of my part. Just to let you know, you have seen a similar picture like this before. We built a demonstrator together with NXT, Peak, and a few other partners. And so in general, everything I've shown here already individually has been proven and shown to work. So there are systems and a demonstrator out there for the NXP secure transceiver, showing that work also in combination with CAN-Crypt and the crypto layer. And we have also done an implementation here together with Axel and his team, where we have then a remote DTLS connection from an Android tablet going to a Bluetooth CAN interface, going to a touch screen, and there's a DTLS communication going here from touch screen to tablet through the Bluetooth layer here. So as conclusion here, again, the recommendation of what's available and what it can be used for. However, as we always pointed out, there's still a lot is application specific, and specifically with the CAN cryptographic layer or security layer that we'll talk about tomorrow, is that we really still need to find easier ways or make easier ways more known on how to handle the key management. Just as a quick outlook, what we do in some the CAN cryptographic layer is that the system can also lock itself and saying, well, we assume that if we are powering up and we do not have a key, that we are still in a safe manufacturer or system integrator environment, and the devices simply generate their own specific key in that cycle the first time the system is powered up, so that it's, so to speak, it locks itself on power up. So this could be one option on how to simplify key generation. Then, of course, there needs to be one method to identify yourself towards the device later for maintenance or so, but there are solutions for that also. With that, I've reached the end of my part of the presentation.